Well, thank you, Tim. Well, thank you, Tim. And again, let me just perhaps emphasize and thank Tim and Will and Thomas in particular for all their efforts in making this such a very successful conference. So thank you. And it's a great pleasure to be here. It's always a great pleasure to talk at these graduate student conferences. It's great to see so many young people who are still kind of interested in geometry, topology, algebra, and its many guises. And contrary to what Yen said in her talk, three manifolds aren't dead just because Ian Eagle. Anyway, so what I'd like to talk about today is going to be arithmetic link complements. And I'm not going to get into any technical details or things like that. It's going to be more of a story, and I'm going to develop some of that historical story as to why we might be interested in such things. I don't know why my screen has just done that, but there we go. But I'd like to start by a quote from Bill Thurston. So this was in his Bulletin of the AMS that, again, Yen mentioned in her talk. So in 1982, Thurston wrote an article in the Bulletin of the AMS, and he listed, I forget how many problems there were, but something like 29 problems or something like that. And as Yen said, well, most of them are solved. There's one outstanding one that needs to be solved to do with rationality versus irrationality of volumes of hyperbolic manifolds. And some of the questions weren't really questions. Some of them were more just, Thurston thinking aloud, and you wrote things down. And what I'd like to quote him here is something that's been a great driver in my mathematical career, and sadly, Tim mentioned 1988, which seems an awful long time ago. So he says, find topological and geometric properties of quotient spaces of arithmetic subgroups of PSL2C. These manifolds often seem to have a special beauty. So these kind of little diagrams on the slides here, I mean, these were going to be link complements that are arithmetic, that have these special beauty that Thurston was alluding to, and I'm going to talk a little bit more about that. Okay, so let me just begin by setting up the scene here. So I'm going to talk, first of all, a little bit about hyperbolic 3 space and constructing hyperbolic manifolds, and then perhaps I'll maybe jump over here to the right-hand side, and I'll motivate the story by talking about things in PSL2R, where perhaps we're a little bit more familiar acting on H2. Okay, so hyperbolic 3 space. So we're going to take the upper half space model for hyperbolic 3 space. So this we view as follows. So this is the complex plane, and this is the positive reals. And we can equip a metric on this space that turns it into a connected, simply connected, constant curvature -1 complete Riemannian manifold, and it's the unique such one. But you need to know about what that metric is. Okay, all you perhaps need to know as far as today is concerned is, well, how do you get, what's the shortest distance between 2 points? Well, the geodesics in this metric space are straight lines that are orthogonal to this complex plane, and semicircles that are, again, orthogonal to this base complex plane. And the codimension 1 sort of geodesic submanifold, so the planes in this space, these are going to be Euclidean planes that are orthogonal to this complex plane, and hemispheres that are centered on the complex plane. So that's kind of what this metric space looks like. And the isometries of this metric space have a particularly nice description. So I'm only ever going to talk about orientation preserving things, because orientation reversing things kind of freak me out. They really kind of make me nervous. So I'm going to stick to orientation preserving isometries of hyperbolic 3 space. And with this model, it's given by PSL2C. Now, just because it's the sort of boy that I am, sometimes I will just forget about this P here and think of matrices. So what is PSL2C? Well, SL2C is just 2 by 2 matrices. Complex entry is determinant 1. P means divide by the plus or minus identity. That is the center. But really, I just think of these as matrices. Okay. Now, how does PSL2C act, you may well ask? Well, it acts naturally on the complex plane, union infinity, by linear fractional transformations. So there's the linear fractional action. on C union infinity, and that just sends Z to AZ plus B over CZ plus D, if that's the matrix ABCD. And well, how is this extended? Well, you know, since we were small children, we've been told that these Mobius transformations can be viewed as products of inversions in circles and reflections in straight lines in the complex planes. So therefore, we can extend that action, i.e. this is the Poincare extension, where we then take reflections in the Euclidean planes together with inversions, so reflections in this hemisphere. That extends the action naturally to hyperbolic 3 space, and that, once one does the calculation, shows that, in fact, PSL2C preserves this metric, and in fact, one can show that it is the full group of orientation preserving things. So that's the action, and that's the group of orientation preserving isometries. Now, for us, a hyperbolic manifold is going to be obtained as a quotient of hyperbolic space. So in our algebraic topology classes, we learn about actions of the fundamental group on the universal cover. You quotient out, you get nice topological manifolds. Here, there's some geometric data that's encoded by this. So what we want to do is to take groups that are acting nicely, and by this we mean, as usual, properly, discontinuously, and freely. So properly discontinuously just means it acts efficiently on this space. It moves compact sets off themselves, except with some finite error. And acting freely means the only element that fixes a point is the identity element. So we want gamma is going to be a subgroup of PSL2C, which is going to be acting properly discontinuously and freely. And the quotient then is a hyperbolic 3 manifold. Okay, it's not just a topological manifold, but it carries a metric that comes from the quotient by hyperbolic space by this group. Now, for us, I don't care about, you know, any old quotient today. I really care about those that, you know, are going to have finite volume. So I'm only going to be interested in let's say M, which will look like H3 mod gamma, having finite volume. Now, what does that mean? Well, if we think again sort of very naively about what this means, this group here, it's some discrete group inside PSL2C. It's acting properly discontinuously and freely there. How do we think of that? Well, there's a fundamental polyhedron that encodes the action for that group. So there's this polyhedron in hyperbolic space for which this quotient is obtained by identifying faces of that polyhedron. It's the quotient space. And that polyhedron tessellates, i.e. it covers, without any sort of nonsense along faces, the hyperbolic space under the action of the group gamma. Okay, so that fundamental polyhedron, if it has finite volume, this guy is called a finite volume hyperbolic 3 manifold. So I'm only interested in, I'll repeat myself, only interested in having finite volume, i.e. finite volume fundamental polyhedron. And we'll see some pictures shortly about, you know, what else that might mean. But that's the setup of what hyperbolic 3 manifolds will look like. They're just going to be quotients by discrete subgroups of PSL2C. Now, as it turns out, the case of acting freely, we can weaken a little bit. Okay, so we're allowing the groups now to have elements of finite order. So I don't know how far I can push that without, well, you can see this part. So we also allow gamma to contain non-trivial elements of finite order. And again, we'll see shortly some examples of how this arises naturally. Non-trivial elements of finite order, so-called elliptic elements. So this will have fixed points on the action in H3, so we don't get the free action, but it's not so bad, in fact. And again, up to finite sheeted covering spaces, we can get rid of this. So this is not a big irritation, but what I'm about to say shortly, this is a very natural thing to allow when we look at hyperbolic three manifolds and things that are almost like hyperbolic three manifolds. So these are called, so in this case, if we take such a quotient, and we look at H3 mod gamma, we get a hyperbolic three orbifold. And we'll see pictures shortly of such examples. Okay, so again, without getting too much into this, so back in the day, when I was a small boy back in Scotland, Thurston was proving great theorems. And he proved that most three manifolds are hyperbolic. Okay, so hyperbolic geometry is the prevalent geometry that we should all, that's probably a hope, just because my computer. This looks like it's a connection, is it? That's good. Okay, thanks. Right, so most three manifolds come equipped with hyperbolic geometry. One can make that very precise, and I'll maybe say a little bit more about that when I talk about link complements. But for the minute, what I'd like to do is move over to dimension 2 and develop the story of what I'm really going to be talking about here today. So H2, again, without repeating ourselves too much, here's the hyperbolic plane. It comes equipped with a metric again. These are the geodesics that we get in the metric, and the full group of orientation preserving isometries is PSL2R. Now, if you're out in Philadelphia one evening and the bouncer stops you at the bar and says, give me an example of a discrete group inside PSL2R, well, your first inclination would be to give the example of PSL2Z. Okay. The reason being, well, Z is a discrete subring of R, and so there's no real prizes for seeing that PSL2Z is a discrete subgroup of PSL2R. Now, what's much more interesting here, of course, is that, whatever an arithmetic group might be, and this is kind of what's been mentioned several times during the course of the conference, whatever an arithmetic group might be, that is one. Okay, and God help us, if that's not arithmetic, we may as well just stop and all go home. Okay, so that's an arithmetic group. That's the thing that we should think of when people say an arithmetic group. And one of the things that we like about it, apart from the fact it has this nice visual description in terms of matrices with integer entries, is that we understand the quotient space under the action of PSL2Z on H2. Now notice that, inside here we have the following element. So this translates by 1. And so just to kind of give some indication here, so what's that sort of saying here? Well, if we take a point here and a point here, so maybe this is minus a half and this is a half, well, these two get identified by that translation. Now in the hyperbolic metric, let's not say too much about what it means here, but when we're very high up the y-axis, the distance, the Euclidean distance is divided by height. So these are very, very close in the in the hyperbolic metric. So the hyperbolic metric is Euclidean divided by the height. So these 2 points, as we sort of zoom off up here, are getting very, very close when you identify by this element here. We also have the element 0, 1, minus 1, 0, and if you square that, you get either the identity or minus identity. Anyway, PSL2Z, it's the identity. Okay, so that's an element of finite order living inside PSL2Z. So this group here, whatever it's doing, it's got this element here, it's got this finite order element here, so there's some complexity to the action of this group on the hyperbolic plane. However, I'm sure we've all seen this, and probably going back to our days in our mother's arms when she drew the fundamental domain for the modular group acting on the hyperbolic plane. So that's kind of the picture that we have here, that these two faces here are identified by this element here, and then there's this little identification that you get from this guy here, 0, 1, not that it matters, minus 1, 0, so those two faces get identified there. So in the quotient, what we see here is, well, we get this thin part that we get by quotienting out from this part. As I mentioned, these points are getting closer and closer in the hyperbolic metric. And then there's this guy here, right? This is a fixed point of this element, so it's going to project down to something that's, It's not a manifold near that point. It gives you some cone angle, and I'm just going to write cone angle. I'll just put a 2 here to indicate there's an element of order 2. And in fact, there's another guy here that gives us a cone angle 3 that comes from these 2 points being identified there. So the quotient of this hyperbolic plane by this guy, maybe write it like this, it's just a disk with a cone point of order 2 and a cone point of order 3. Okay, so that's what the quotient space looks like for the action of PSL2Z. Okay, we're okay with that. Okay, well, I promised you manifolds, and we can easily arrange manifolds. And how do we do that? Well, you see, the good news is that, for example, we could take the level 2 congruent subgroup. So let's write it here. So gamma 2, this is the group generated by 1, 2, 0, 1, 1, 0, 2, 1. And a picture of a fundamental domain for this guy looks like, so this is 0, minus 1, 1. So this guy is identified there, and these guys are identified here. And this turns out to be a torsion-free subgroup, so there are no non-trivial elements of finite order here. And the quotient in this case is, well, these two sides get identified, but we still have these cusps here, one at infinity. There's one that goes down to this real line at infinity. These two guys get identified, and then we've got this guy. So what we see here for this guy is a 3 times punctured sphere. So H2, 1 gamma 2 is equal to this 3 times punctured sphere. Now, as has been mentioned several times, these congruent subgroups that arise, so gamma 2 is given in the modular group by these matrices, but as Jordan mentioned and others have mentioned, that in general, you know, God hands you a collection of finite index subgroups of linear groups. This is one of the great things about linear groups, and you should never forget that, because once you go outside the world of linearity, it's really quite a challenge to find subgroups of finite index. So let's just recall the following picture, congruence. Subgroups. So let's let n be bigger than or equal to 2 be integer, and we'll let gamma n to be the kernel of the map PSL2Z to PSL2Z mod NZ. Okay, so these turn out to be nice finite index subgroups. Well, the finite index, that's easy to see. This is a finite ring, so therefore that thing's a finite group, so it's finite index. And it turns out that these things are all torsion-free, so they all act freely on the hyperbolic plane, and they give you quotients of the hyperbolic plane that are, well, maybe they don't look like this, but they're 2-dimensional manifolds, and they have punctures, so they look like some genus G surface with punctures. That's what these quotients look like. And a group is called, so gamma in PSL2Z is congruence if gamma contains a gamma of n. Okay, now I'll come back and say a little bit more about the fact that being congruence in this case is a very special phenomena. Okay, so maybe now I want to sort of switch back again to talk about the 3-dimensional setting. So PSL2Z, okay, that is the very first example of something you would think of as a discrete group inside PSL2R. It also comes with arithmetic connotations. Okay, so you've been to your first bar, and they've asked you about there. You go to the second bar, and the bouncer says, okay, give me a discrete subgroup of PSL2C. Okay, so it's maybe a more advanced bar. It's probably maybe a cocktail bar or something like that. So you want a discrete subgroup of PSL2Z. Well, you think to yourself, well, if I take PSL2 of the Gaussian integers, so Z adjoint I, this is just the collection of guys, A plus BI, where A and B are integers. Okay, so again, Z adjoint I, that's discrete inside the complex numbers. So PSL2 Z adjoint I is going to be discrete inside PSL2C. So that's good news. There you constructed a discrete group. Well, in fact, there could be an infinite pub crawl at this point, because instead of just doing this one, you would say, well, I want something more complicated. Well, the right way to say this is the following. It's the so-called family of groups that are called the Bianchi groups. And here we take D to be a square-free positive integer. And then we take OD inside the field Q adjoin the square root of minus D. So this is the ring of integers, of algebraic integers. In Q root minus D. Now, I maybe don't want to get in this, define this right now, but it's just everything. Okay, let me just say, I guess we're on camera, so we have to be careful and not lie too much. But these are algebraic numbers in Q root minus D. They satisfy some polynomial, ax squared plus bx plus c is 0. And the integer ones, those are guys where a is equal to 1. So they satisfy monic polynomials of this form. So that's what the ring of integers looks like. So in the case of z adjoin I, what I wrote down is precisely that ring. If you take d is 2, you get z adjoin root minus 2. And then there's a little bit of excitement at d equals 3. You might want to write down z adjoin root minus 3, but you wouldn't be quite right, but you wouldn't be far off. You would take z adjoin omega, where omega squared plus omega plus 1 equals 0 is a root of unity. So the Bianchi groups, they're some class of examples that, I haven't told you what they are yet, have I? That would be useful. So you can probably guess what they are now. If you look at OD, these are all discrete subrings of the complex numbers. So OD in C, this is discrete. And then PSL2 OD inside PSL2C. These are discrete. Okay, so this is a nice collection of discrete subgroups of PSL2C that are kind of are described arithmetically. Okay, they come using the number of theoretic entries to describe the group. Okay, so then you ask, well, what does H3 mod PSL2OD look like? So let's call this, or let's call this gadget here Q sub D. So I almost said the word orbifold. It is an orbifold. Well, why? Well, notice that PSL2OD contains PSL2Z. So Z is a proper subring of OD. So PSL2Z, this guy here, lives naturally inside PSL2OD. So that group, therefore those elements, live inside PSL2OD. So whatever the quotient space is, in terms of the action, okay, we still have that element, and we still have this element. So we see some orbifold kind of stuff. And we see this stuff, so we should still see some points that go off to infinity. Okay, so let's see how we get on. So, so here are some pictures that we're going to talk about. So let me try and explain some of what's in these pictures. So you'll see here, oh, here we go. So there's d equals 1, d equals 2, d equals 3, d equals 5, d equals 7. Okay, so there's stuff that's purple. That's the analog of these red dots here. So that's the singular locus that you get from the image of the stuff that's finite order acting on H3. Okay, so here we see 2s and 3s, and you only ever see 2s and 3s for reasons that I won't explain. Now, in the case of d equals 1, so this is meant to be kind of a two-sphere, like a ball with arcs in it. D equals 3, that's meant to be a ball with arcs in it. Here, this guy here, this is meant to be a solid torus with arcs in it. And here, we've got solid torus with arcs, and then another torus that's buried inside the solid torus. What the heck does that all mean? Okay, let me try and explain that to you. So let's think about the modular group picture once again. So when we drew this quotient here, what we see is that we just have one cusp here. So there's just one cusp. Now where does that one cusp come from? Well, it comes from here, right? This point at infinity. So what this is really telling us here is that PSL2z, if we look at the orbit of infinity here, this turns out to be the whole of the rational numbers union infinity. So if you look at things that are, so we have parabolic elements in PSL2z, they fix points in Q union infinity in the boundary at infinity. Okay, so the orbit of this point in infinity is really picking up the location of all the cusps when we lift to the universal cover. So the fact that we just see this one orbit of infinity, and why is that? Well, this is just a Euclidean algorithm. If you give me an A over B that's in the rational numbers, and I want to make that a parabolic fixed point, or the image of infinity, so I want T of infinity to be equal to, let's put C here just to be consistent, A over C, well, A, C, B, D. I can find, using the Euclidean algorithm, a B and a D such that AD minus BC is 1. Okay, so everything is equivalent to infinity under the action of PSL2z. So that's what this picture is really saying. There's one cusp because everything's equivalent to infinity. Now, what does that really say? It's saying we're using this Euclidean algorithm. That means that, as we know, Z is a principal ideal domain. So what we're seeing here for these different so for these guys here, so we're seeing that, well, I'll say in a minute what this really represents, but the fact that there's only kind of one thing here where there's two here, this is getting into the situation where when D is 5, this number field here fails to be a principal ideal domain. Okay? And the number of cusps that you see is a measure of how much you fail to be a principal ideal domain in this particular field. The field theory shows up naturally in the quotient space by counting the number of these so-called cusps. Okay, so what does this picture mean? So again, let's think of a schematic. So we've got a schematic for this Bianchi orbifold QD. Okay, so we may have more than one cusp. So there's some sort of excitement in here, there's maybe some topology, and then there's maybe some singular locus that we have to understand. Okay, so what's going on at infinity? Why do we see, in the case of d equals 2, just the solid torus, and in d equals 1, d equals 3, we see sort of the ball. So again, let me just say what that picture is really representing. So here's the picture for d equals 1. We've got this ball here, and then we've got arcs. Again, something like this. So this is meant to be a cross section. So if we're flying out a cusp here, and we just stop things at some point here, what we see is a cross section. Okay, so this is really the compact manifold or orbifold with boundary, and the boundary is what we see at this point here. And in this case, we see a sphere that has 4 marked points that come from a Euclidean structure on the sphere with 4 marked points of order 2. Now, where do these come from? Okay, the point is that Z adjoin I has extra units, namely plus or minus I. So if you look at the stabilizer of infinity in this Bianchi group, it looks like, well, this guy, actually, let me write it down here. It looks like this guy, and then there's this elliptic element that's also in here. So because of these extra units, you get guys that fix infinity. That has to show up in the cusp. That's why these two guys here for d equals 1 and 3 give you a cross section that's a sphere rather than a torus. So these other guys here you see a torus because there's no extra units. So that's what those pictures mean. Okay, so maybe that went a bit quickly, but the key thing to take away here is that the cusp shape of these orbifolds Q1 and Q3 is governed by the fact that there's these extra units in the ring, and you get this showing up again in the quotient space of by the Bianchi orbifold. Okay. Now, back here once again, the modular group really encodes all the arithmetic. Yeah?
Will you get, in general, as many, like in the D equals 5 case, as many red guys as there are?
Right, so if the class number is 20, you'll see 20 tori showing up like that. That's right. And there's only, so there's only finitely many guys that have one cusp here. So that's a solution to the class number 1 problem, for which Baker won the Fields Medal. And so you only ever see finitely many of a given number of cusps here. So the number of cusps goes to infinity very, very quickly. Okay, so the collection of arithmetic Fuchsian groups that have parabolic elements are really, it's really just a modular group up to some degree of error called commensurability. And once again, the Bianchi groups, give us all the arithmetic Kleinian groups that have these parabolic elements. So there's closed arithmetic hyperbolic manifolds that I'm not going to talk about today. These don't have parabolic elements, but all the guys that do have parabolic elements come from the Bianchi groups. Okay. So now let me get on to talk about what the title was about, link groups. So let's, again, keep jumping back to the modular group, but that's kind of the nice picture. So we had this example of H2 mod gamma 2, which was just a 3 times punctured sphere. So what's the analog of a punctured sphere, 2 sphere in dimension 3? Well, we take the 3 sphere, instead of puncturing it, we remove some link from the 3 sphere. Okay, so link is just some embedding of circles into the 3 sphere, and look at the complement of that. So what we're going to look at now are link complements. These are the analogs of the genus 0 surface groups inside the modular group. So I want to talk about arithmetic link complements. And for the purposes of today's talk, let me just define them to be links in the 3 sphere. So this is i.e. L contained in S3, so that S3 minus L is a finite sheeted cover of QD, i.e. the link group pi1 of S3 minus L lives inside some Bianchi group of finite index. Now, we saw some at the start. So let me just see here. What's next? Oh, okay. So here are some examples. And for those that have looked at Thurston's notes, I mean, they should be very familiar. Have you broken it, or? Oh, it's maybe that one. Oh, it's that one. Okay, I was using the wrong one. Sorry about that. Okay, so this here, that's the Whitehead link, and what we're saying is that this Whitehead link complement covers the Bianchi orbifold with D is 1. This is the figure 8 knot complement, and we're saying in this case that the figure 8 knot complement covers the Bianchi orbifold when D is 3. And Thurston studied these in detail in his original notes, and we're really kind of, the figure 8 knot in particular, were kind of really sort of inspirational for his understanding of hyperbolic structures and geometric structures in general. This is a guy D equals 2 that you get, that one can just compute to find a faithful discrete representation. And this guy is D equals 7. So this guy, for future reference, in Texas, this is called the magic manifold. No, maybe it's not called the magic manifold. It's called the magic manifold here, because Dave's in the audience. So it's called the magic manifold because it's got various magical properties to do with exceptional Dane surgeries. So, one of the things that Thurston noticed when he made that quote about having arithmetic manifolds having extra properties, these manifolds here, in particular this guy, and this guy, all have special roles to play in various aspects of three-manifold topology, and in particular this one, the case of so-called exceptional Dehn surgery problems. So these arithmetic link complements here, they seem to be very special examples. Okay, now Thurston proved in a very precise way when a link complement admits a hyperbolic structure. And again, I could say the real thing, like, okay, if as long as it's not a torus link or a satellite link, then it's hyperbolic. Okay, you should take away that most links in the three-sphere, the complements are going to be hyperbolic manifolds. Now, what you may think of as well, how about arithmeticity? Well, arithmeticity is certainly a very special thing. So for example, yeah, the figure 8 note here, this is the unique arithmetic knot in the three-sphere. And there are an awful lot of knots that admit hyperbolic structures. But nevertheless, these manifolds that are arithmetic link complements seem to be very, very special. So here's some for d equals 1, 2, and 3. So let me state now a theorem that gives extra support to the statement that these arithmetic links are quite special. So going back to the 8A's, and again, maybe I won't go into this in detail, there was the so-called cuspidal cohomology problem that was solved. So let me just put it here, lots of Germans, and then Volkmann. Now, this is Karen Volkmann, and just in case, yeah, she's not German. Okay, so there's lots of Germans and Karen Volkmann, and what they proved was that if you have a link complement that's arithmetic, so it covers one of these Bianchi orbifolds, then D is really heavily restricted. Belongs to 1, 2, 3, 5, 6, 7, 11, 19, 23, 31, 47, 71. So there's 14 values of D for which you can be an arithmetic link complement. So all these other Bianchi orbifolds, I mean, somehow topologically, they're really, really complicated. That's kind of the punchline of what this theorem is saying. Whereas the only ways you can see a link complement is if you're in this case here. Okay? And Mark Baker proved, in fact, there exist links for all such D. Okay, so we've seen some here. Right. So this is some, d equals 1, d equals 2, d equals 3, and you'll see some more later, d equals 7. This is 31. Okay. So that's kind of splendid. And what's kind of cool is you can really go in and check with Snappy. This thing, is what I say it is. And, the way that Mark does this is, you go to the orbifold Q31. So it's got several cusps. It's got several bits of singular locus. And he gets down on the floor in his office. I've seen this with my eyes. And he has, mountain climbing string and desingularizes the orbifold. And you get that picture when D is 31. And then, more splendidly, 47. It kind of looks like this. So you can see that's kind of very splendid kind of examples. And I think for 71, I'm not sure that a human's ever seen a link that, exhibits Baker's theorem. We know they do exist, but it's hard to draw a link complement for the case of D equals 71. Okay, so we have these links. Now, in fact, there are infinitely many arithmetic link complements. So maybe just let me preface that by saying that there, if we go back to the modular group picture once again, so we have this genus 0 surface there, and you just note there exist infinitely many gamma and PSL2Z of finite index, so that H2 mod gamma is equal to a sphere with punctures. Okay, so the number of punctures will grow to infinity, but there are infinitely many. How does one see that? Well, you could take H2 mod, you could take the group gamma 2, and let's just assume that it's generated by the two elements A and B, and you could surject onto Z and surject onto Z mod NZ, and maybe we send A and B to a generator here. And if you just think about this for a minute, you can just do the covering space theory to see that the covers induced by this n-fold quotient are indeed spheres which are multiply punctured. So there's infinitely many genus 0 surfaces that arise as surface subgroups of the modular group, and there are infinitely many link complements that arise as subgroups of the Bianchi groups. I think it's the other one. Let me put this over here, otherwise I'll get confused. Okay, so we've seen that. Okay, there are infinitely many. So how do we do that? Well, the way that we do that is that if you take suppose you've got some link complement here, so here we go. So that's just another picture of the Whitehead link. So one can think of taking a homomorphism to Z like we did over there, for which this generator here, this kind of meridian element, maps to a non-trivial element, a generator, say, of the Z, and then this guy maps trivially. So all of these guys left, and then the preimage of this guy is connected, and what you see is a link in the 3-sphere. Basically, your branch covering S3 over this unknot, so you get S3, and then you remove the preimages. So you get infinitely many links in the 3-sphere that are still arithmetic. Okay. Now if we go back to the so I want to go back to the modular group again. Okay, let me leave that there for a minute. So let's just sort of summarize so far. So there's infinitely many arithmetic links in the 3-sphere. They all cover these Bianchi orbifolds that go from 1 through to 71 as listed there. Now, what happened in the case of the modular group, and this is kind of the theme of the story, is that back in the day, people were interested in to what extent the congruent subgroup structure of the modular group saw the various kinds of surfaces. So these guys here give genus 0 surface groups, or punctured, I should say. And Rademacher, in the late 50s, early 60s, asked a question as to what extent congruent subgroups in the modular group could have genus 0. Okay, so it was a question of Rademacher. So let's just say in the 60s, are there only finitely many congruence subgroups of PSL2Z of genus 0, meaning that we look at these congruent subgroups here, we look at the quotient, and we want those to be punctured spheres. Now you could even ask for fixed genus, in fact, or a fixed genus. Now, if you think about this for a minute, you think, well, that can't be so hard. And it's not hard to prove, so we'll maybe talk about this shortly, but let me just leave it as an exercise, that for principal congruent subgroup, it's easy. So for principal congruent subgroups, you get genus 0 if and only if n is 2, 3, 4, and 5. So we've seen the n equals 2 case above. Now we're dealing with Fuchsian groups here. So you think to yourself, well, we're Fuchsian groups inside the modular group. That's just free groups. Okay, so surely we'll be able to figure this out, determining when things are genus 0 or not. But it actually turns out to be, it's not deep, but it's tricky, in fact, to prove this. But that was proven, so the answer was yes by Denin in the 70s. Now there's a fancier way of proving it that's much more elegant these days. It uses the first non-zero eigenvalue of Laplacian, but I'm certainly not going to get into that. But the point is that these guys here that come from maps to Z, these are never congruents, okay, after a certain point. So these guys are not congruent subgroups. So this genus 0 guys, they don't give this kind of construction of congruent subgroups of genus 0. So the answer was yes, and you may wonder, well, you know, what are they? Well, let me show you what they are. Okay, so there are 33 guys inside the modular group that have genus 0, and here's the list. So as you can see, the ones in red there, they're the principal congruence guys of genus 0. Now, let's just think about this for 1 minute. So let me give you a little hint as to why you might believe that 2, 3, 4, and 5 are relevant here. So if you think of the modular group, we have this element in PSL2Z, so let's call that T. And if we look at T to the n, which is 1, n, 0, 1, this lives inside the principal congruence subgroup of level n. Okay, we reduce mod n, that's 0, so that's the identity. Okay, we didn't argue that. But now then, what one needs to show is that you really need to show that gamma n is equal to the normal closure of T to the n in PSL2Z, i.e. the smallest normal subgroup you get when you take conjugates of T to the n inside PSL2Z is this principal congruence subgroup of level n. So if you can show that, then you're in business. And in fact, that's why n is equal to 2, 3, 4, and 5, because notice that if you look at the group A, B, T, a squared is b cubed. Well, now T to the n is 1, T to the n is the identity. So this is a triangle group, and this is finite only when n is 2, 3, 4, and 5. So that's the reason why you see that this congruent subgroups are principal congruent subgroups only in the cases of n equals 2, 3, 4, and 5. It's really the fact that you need the normal closure of this element to be the whole of the principal congruent subgroup. Okay, so that's PSL2Z. What about a generalized Rademacher statement? So let's do that here. So what about dimension 3? So is there a generalized Rademacher result? I.e., we've seen there's infinitely many arithmetic link complements. Are there only finitely many congruents? Arithmetic link complements. So let me just say a quick word about some of the words in the definition there. So we've seen congruent subgroup several times now in principal congruent subgroup. In this case, what we do is take reduction modulo an ideal. So let's call this pi sub I. Then let's let gamma I be the kernel of pi sub I. So again, this is a finite index normal subgroup of the Bianchi group, and a group is called congruence if it contains such a guy of finite index. And the question is, can we fit link groups into this picture? Okay, so that's the question we'd like to ask. So now, Thurston was an amazing guy, okay, and occasionally he would just send me an email, and you know, I would see where the email came from, and I thought, I'll better lie down before I read this, because you know, I know it's going to involve some serious thinking. So he sent me this email back in 2009, and he understood about arithmetic link complements. He says, although there are infinitely many arithmetic link complements, there are only finitely many that come from principal congruent subgroups. So here we're talking about just congruence, but like the situation here, there are only finitely many principal congruent subgroups. So a little argument shows that, and Thurston knew this as well, that in fact there are only finitely many. So it's a fairly straightforward little lemma that there's only finitely many principal principal congruence link complements. So it's an argument that's a variation of the argument that I gave over there. So Thurston knew this, and we exchanged some emails about this, and he was interested in what the complete list is. So that's kind of what I'd like to finish up with, just talking a little bit about some work with Mark Baker where we're trying to complete this list. Okay, so what are the principal congruence link complements? So here's some examples. So again, this was taken from work of Baker a fairly long time ago now. So there are some very nice examples of d equals 1 and d equals 2. And these are level 2. So the ideal here in those examples, so that's the level. So here the ideal is just the principal ideal that's generated by 2. And this guy 3, that's a fine example. And d equals 7, and we can go on. Now the magic manifold turns out also to be congruence, principal congruence. And you can just see that by just checking that the group is generated by guys that are sort of visibly, so here the level is 1 plus root minus 7 over 2. And if you look at 2 in this ring, it looks like that times its complex conjugate. So this thing here is congruent to 0, that's 0, that's 0, modulo that ideal. So in fact, this guy here on the nose is this principal congruence subgroup of that level inside the Bianchi group PSL 207. Now here's some more complicated examples for other rings. So D is 15 and 23. So these guys are not principal ideal domains for d equals 15 and d equals 23. And so hence the ideal is a little bit more complicated. It's not generated by a single element, but because it's a Dedekind domain, you can find 2 elements that generate. And so for 15 and 23, one can build the principal congruence subgroups to be these link complements. And again, how do you do that? I mean, you really have to get down there and build that sucker, okay? There's a quotient space here. Somehow you've got to prove that that quotient space is homeomorphic to that link complement. So that can involve a fair amount of pain and suffering, especially if you're called Alan Reid. So these are kind of non-trivial exercises to push that through. Now Thurston, again, was an amazing guy. I mean, and he just happened to notice when he was doing something else completely random. Well, it wasn't completely random, but it was completely different from what this was about, i.e. principal congruence links. This was looking at triangulations of manifolds, and he kind of noticed that if you look at, there's this like 1, 2, 3, 4, 5, 6, 7 circle chain here. So you'll if you cast your minds back, there were a few circle chain links that were congruence link complements that showed. So Thurston drew this one and didn't see that it was congruence, but he had the foresight to understand that if he drilled out this little guy here that ran around, that's going to be congruence. And that's what he proved. I mean, he should have explained that to me at some point. And it's just kind of a really cool construction. So the norm here is 7. So 25 plus 3 is 28 divided by 4, that's 7. So this is a cover, the link complement here is a 168-fold cover of the Bianchi orbifold. Now 168 might strike you, right? Because that's the finite simple group PSL2F7. And that's really what Thurston was looking at. He was looking at interesting actions of PSL2F7. So if you think in the case of Riemann surfaces, Klein's quartic is a surface that admits a PSL2F7 as a group of isometries. And Thurston was thinking about that and came up with this example that was an analog, for him at least, of this Klein quartic. So that's another very beautiful example of Thurston's. And so he kind of said to me, well, one of the most intriguing congruence covers I know is the ideal generated by blah, blah, blah. And in fact, he knew lots of other ones. He just didn't tell people. So even in his notes, if you look at his notes, there's this rather fine example here where you've got this 4-component link. And again, one has to prove it, but you can check that it turns out to be this. Ah, there it is. It turns out to be inside the Bianchi group, d equals 2, and the level is 1 plus root minus 2. Now, he didn't know it was congruence or principal congruence, but he surely knew, just because, he just surely knew. And then there's another very fine example in Hatcher. There's a very beautiful paper of Alan Hatcher where he gives decompositions of certain link complements in the 3-sphere, this is back in the 80s, into certain polyhedra, and use that to build interesting arithmetic examples. And so here's another example of that turns out to be principal congruence when the Bianchi orbifold is Q11. Okay, So there probably isn't going to be any comments on the strategy of Baker-Reid, but let me just maybe finish by saying what the state of affairs is for principal congruent subgroups. So let me just maybe state a theorem. So this is, so let me just state this as kind of a vague theorem. That's not to say that it's not been proven. It is proven, it's just vague, and I'm not going to give you the gory details. So the first thing is that there exists congruence link complements for every D. For D equals 6 and 39, there are no principal congruence links. But all of those have. There's a complete list of principal congruence link complements when D is 1 and 3. So this is stuff that I did with Baker. This was done by Matthias Görner, who was a former student of Ian Eggles. And there's a complete list when the class number, i.e. when you're not a principal ideal domain. So whenever you've got class number bigger than 1, so there's more than one cusp to the Bianchi orbifold, you can prove that. So that's kind of part of it. There's still things to do, in particular for the class number 1. So that's the case that we'd really like to understand. We'd really like to prove, or the analog of Rademacher's conjecture for congruence links. So we would like to prove there's only finitely many congruence link complements in the 3-sphere. Now you can even generalize this to ask for congruence link complements in any closed 3 manifold, and that would still be interesting. And so I think maybe I'll just stop by saying that the takeaway is here that there's this wonderful mix of geometry, topology, and number theory buried in the Bianchi orbifolds and their subgroups of finite index. It's a lifetime's work, the Bianchi groups, and I encourage you to think about them. They're great examples. I'll stop there. Thank you.
Any questions? I had one.
Yeah.
So it seemed like, I'm not 100% sure, but it looked like all the link complements that were up there, the components were all unknotted. Is there some reason why?
No. There are examples that are knotted.
Okay.
But why these particular principal congruence links seem to be awash in these unknotted components, that's been a mystery to us as well. Yeah.
Can something be said about the symmetries of this?
Sorry.
Can something be said about the symmetries of these arithmetic links? Because the example that you showed, some of them are very symmetric.
Right. So for these principal congruence links, they've got a large symmetry group because their fundamental groups arise as normal subgroups of the Bianchi group. And in fact, they are normal often in bigger groups as well. So that's one of the reasons that Thurston was interested in these principal congruence links. He was interested in links that had huge symmetry groups. And again, that's another interesting aspect of these link complements. They tend to come awash in symmetries. Maybe there's one, I forgot if I showed one, there was one other comment of Thurston's I meant to show. Did I? Maybe it's back. Yeah, so Thurston, again, when he was in an email, he was just interested in these principal congruence links because somehow when he was doing his experiments, so Thurston was a great experimenter, and when he was doing his experiments, he would see things that would give him these principal congruence links for no reason whatsoever. So for example, as he said, they seem to be amongst the most general given their volume for producing lots of exceptional manifolds by Dane filling. So exceptional manifolds are things that are not hyperbolic. And again, as I mentioned at the start, these arithmetic links that show up here, they seem to be very useful for constructing non-hyperbolic Dehn fillings. Yeah.
These are the natural generalization of genus 0 surface groups.
Right.
What about like genus 1?
So, I mean, you could just sort of, so again, you could just ask more generally. So once you get beyond genus 0, so, I mean, genus 0 you could think of as, well, maybe it's links in the 3-sphere or it's links in integral homology 3-spheres, but let's stick with links in the 3-sphere. You could then just ask conditions on homology, you know. So like you go to the torus, you see Z cross Z. So you look at links in the complement of something that has got some condition on homology. Or links in guise of Hagar genus 1, for example. So there are various kind of ways to generalize that. But I think just asking the statement, you know, if you fix a closed 3-manifold, what can you say about arithmeticity of links? So every closed 3-manifold contains an arithmetic link. That's another thing to say. Every link is the sublink of an arithmetic link. So they can be quite complicated. But I think just trying to organize closed 3-manifolds via the arithmetic link complements is something that would be useful, especially in light of that Rademacher conjecture. Yeah?
Would you expect a kind of like principal finiteness to hold there?
So,
For any fixed genus?
right. So in fact, that is a theorem. So this theorem for the 3-sphere, that's very easy, basically. I mean, it's really just a consequence of the 2-pi theorem. But if you fix the closed 3-manifold now, former students of mine, Chris Leininger and Grant Lakeland, proved in fact the same result holds, that there's only finitely many principal congruence link complements in any fixed closed 3-manifold. And there, the techniques that one uses are systole bounds. So link complements in the 3-sphere, there's an upper bound to their systole, the length of the shortest closed geodesic. So Lakeland and Leininger have an argument that's based on that kind of observation.
Let's thank our speaker again.